Here, yes, we are recording now, I think.
Yes, it's recording.
Yes, yes, we are recording now. Okay. Yes, now we don't have, yes, because all the time they are changing this platform. And remember, before was indicating the time, but now it's not indicating the time. Can you confirm if we are recording now? One of you, please.
Let me see where it shows that it's recording. I cannot see.
Yes, I cannot.
I see I see a dot, a small dot. I don't know if it's recording.
Okay. I think it's a recording. I think it's recording. Joel, you know, is recording the Ruranil?
I'm sorry?
Okay.
Yes, Professor. It
think
says
it's recording.
recording.
Yes, it's recording.
Recording, yes. Yes.
Okay.
Okay, then.
Okay, thank you. Okay, let's go to start then. Yes, good morning for everyone. Okay, today we have a seminar from Professor Gustavo Vicente from the Universidade Estadual de Rio de Janeiro. Okay. Professor Gustavo Vicente is an specialist in cosmology, quantum cosmology, and inflation. Okay. And then the title from his seminar is Pre-inflationary Dynamics in Quantum Cosmology in the Broglie-Bohm interpretation. Professor, you have the word, please.
Thank you. Thank you, first of all, for the invitation. Thank you very much, Professor Giovanni. Well, I will talk about pre-inflationary dynamics in quantum cosmology in the Broglie-Bohm interpretation. So I will talk about inflation, I'll talk about quantum cosmology, and quantum cosmology in this specific interpretation of quantum mechanics. I know from Professor Giovanni that you are used to look quantum cosmology, so now it's a different aspect of the quantum cosmology. Well, these two papers are the source for the presentation. So this first paper was done with a student, a master degree student, Victoria, and with my collaborator, Professor Rudney Ramos. And this second paper was done with another student, Renato Silva, which is actually a PhD student. He is still doing his PhD, and also the collaboration of Professor Nicole Benetti from University of Napoli, which is responsible for the numerical part, the computational part, the observational part. So these are the main articles. Here is the background, and here is the perturbation part. So a little overview of the subject, then quantum cosmology and this specific interpretation, then the constraints on the parameters of the model, the results from coming from these constraints, and some conclusions and perspectives. So from the beginning, the hot Big Bang model explains well the CMB, the cosmic microwave background radiation, the abundance of the light elements of nucleosynthesis, and describes the large-scale structure of the universe. So it's a good model, but it has some drawbacks, which are mainly flatness and horizon problems, and in the initial singularity. So in the hot Big Bang, you have an initial singularity where physics cannot be done. You have a problem, the breakdown of classical physics. And these problems are very important. Flatness has to do with the fact that the universe is flat, and there is no mechanism that can explain how the universe is flat, why the universe is flat. And the horizon problem has to do with, for example, now we have the temperature of the universe is almost homogeneous in the whole universe, but how can these parts connect to each other in such a big universe? How the one region which is not causally connected to another region knows the temperature is the same. So this is the horizon problem. The first attempt to solve this problem is the inflationary paradigm, where you suppose that in the very early universe, right after the singularity, you have a brief accelerated expansion, a brief time of accelerated expansion. And with this expansion, we solve these problems. The flatness is solved by the stretching of the universe due to the expansion. And the horizon problem, if the universe is too big to connect each part to have the temperature, the homogeneous temperature, if we have an expansion, it means that in the early universe, it was a small universe, so it can connect. Each part of it can connect. And after the expansion, we have the universe of today with the almost homogeneous temperature. So these problems are solved, but not the initial singularity. And also, inflation provides the quantum seeds for large-scale structures. So during inflation, there are perturbations that, due to expansion, are stretched. So these tiny perturbations, which are stretched, provide the large-scale structure, which is present here in the hot Big Bang model. So this is a very successful theory for the universe. These two combined, you have the hot Big Bang model and the inflation right in the beginning of the universe. On the other hand, we can have a bounce. Specifically here, I talk about the quantum bounce. We can have a classical bounce. There are many attempts to study a classical bounce, but the quantum bounce is specifically when we invoke quantum effects to solve the problem of initial singularity. So at the initial singularity, you have a breakdown of classical physics, but it's naturally solved by quantum gravitational effects. So the initial singularity in this setup is replaced by a non-singular quantum bounce. So where you have a tiny place where you have infinite density, you have everything breaking down, you now change it by finite quantities. For example, a great energy density, but finite. Well, and this quantum bounce, if you eliminate the singularity, it means that there is a past. So we have now a finite universe at where we have had the singularity, and before it we have a phase of contraction. So the bounce connects a contracting phase to an expanding phase, which is the one that we observe. So these are the figures. Big Bang and inflation. Big Bang is the whole history of the universe. The singularity is here, and in this white region here, right in the beginning, we have inflation, a very brief period of acceleration that solves the Big Bang problems. On the other hand, we can have a bounce. Bounce is taking this point, considering it here. I think you can see my mouse, the pointer. Here we now have a very small size universe, and here the contracting phase. So the universe contracts to a very small universe and then expands. What about what happens before the contraction phase? We don't know. We simply have this contraction phase. We impose conditions here, and we need, but we don't know the universe before. We know the universe after, right? So we have these different aspects for solving the problems of Big Bang. The bounce itself can solve the Big Bang problems, but both aspects, inflation and bounce, have its drawbacks. And what about considered both together, bounce and inflation? So the first question, they are mutually exclusive. I'm sorry. We can have only one or another. No, we can have a quantum bounce which eliminates the singularity, and also after it a period of inflation. So when you have both together, the bounce eliminates the singularity, inflation continues to generate the large scale structure of the universe. And also now the bounce, which comes before inflation, naturally sets the initial conditions for inflation. There is no fine tuning there. They are naturally set. So this is very important. And you can ask, but that bounce also generates the large scale structure of the universe. Always also generates the quantum seeds, of course. But in this picture, we have inflation as the main source for generating the large scale structure, the spectrum. And the bounce will add effects. It happens before and will add effects in inflation. So this is the whole picture. And I cannot, I have to talk about loop quantum cosmology. Professor Giovanni also told me that you work with this theory, which is very important. In fact, many things that I'm considering here are done in this setup. So we are now exploring what happens in the Broglie-Bohm setup. So we always consider the results of loop quantum cosmology, which is for those who don't know, who doesn't know, it's loop quantum gravity, which is a theory of quantization of gravity applied to cosmology. So loop LQG becomes LQC, loop quantum cosmology. Well, and about what I'm talking about, bounce and inflation. What observable signatures that we can have in this setup? Can bounce physics leave observable signatures? So what I am asking to myself, if inflation generates a large scale structure, what about the bounce that happens before? It will leave some imprint. And which region of the spectrum? Low momentum, high momentum? This is the question. So I will consider the classical model, first of all, and then the background model, the classical background model, and then the perturbations in this same setup. So I consider a canonical scalar field. So in FLRW universe, and here is the metric. Then I consider the Lagrangian with the gravitational part and the canonical scalar field part. The Hamiltonian obtained from this Lagrangian. And at this point, we consider the following. Here we have two canonical momenta that are squared, both of them. But in the next slides, I need to quantize it. And to quantize it, I will need that one of them is linear. So I will select this P phi to be linear. So how can I do it? I will do a canonical transformation and phi and P phi to these new variables T and PT, which is this transformation. And then the Hamiltonian is more simple. So here we have now a linear canonical momentum. The problem is that the potential is now very awkward. It depends on the canonical momentum. But that's okay, this part here. So we will consider that the potential is zero. So I'm studying the part where the potential does not dominate. There's no problem. So potential is zero, and I can obtain these equations of motion. So equations for A and PA, and the equation for PT is zero, the derivative is zero, so PT is constant. And here are the relations between the cosmic time to this capital T, which is another time variable. Well, how do we obtain the classical equations? We set the Hamiltonian, which is here, with potential zero, zero potential, to zero. So by doing so, we have this equation, and using the equation for A prime, we obtain the Friedmann equation. So it's the Hubble parameter squared, and here kappa is the square root of HPG here. So here it's HPG divided by 3. PT is a constant, and here h to the sixth power. When we have here is the energy density, whole. When we have here h to the fourth, it's radiation. H to the third is dust. When we have to the sixth is stiff matter. And stiff matter is exactly how the scalar field with no potential behaves. So this is consistent. The Hubble parameter, the Friedmann equation for stiff matter. And the solution for this equation are in fact two solutions, two disconnected solutions. One for positive t and one for negative t. They do not connect. So we have a solution for positive t, which is the observed universe, and one for negative t, which should be the contraction, but they do not merge to each other. They do not merge here, for example, at a equal 1. No. So if they do not merge, we don't have a connection with the contraction phase. We don't have a bounce, right? So this is the conclusion here.
Professor,
right?
Sorry, can I do the question?
Of course.
Yes, usually we have the problem about the time here, no, in quantum cosmology, and usually we need to include some like a perfect fluid. In this case, you don't have perfect fluid.
Yeah, the perfect fluid. I'm sorry, the perfect fluid is the scalar field.
Yes, but in that case, it's like you are recovering some notion of time, but this notion of time is the same time. This t capital is the same that the t small.
No. T small is the cosmic time itself,
Yeah.
and this t now it is like we change the scalar field to a time variable, which is exactly what we do with fluid. So it's like including a fluid with omega equal 1, a stiff matter fluid. It's exactly the same. I could have begun this whole setup, for example, including a stiff matter fluid without talking about the scalar field. And at the end, I can say that a stiff matter fluid describes a scalar field with no potential. Right?
Yes, okay.
I am in fact including a fluid.
Okay.
The Schutz formalism, all that stuff that we have, include a fluid, and then the time variable comes from the fluid.
Yes.
Exactly this.
In the case of the perfect fluid, usually you obtain that t equal to t small, something like this, no? But in this case, you have dt and integration, I think. But in any way, you can solve one in function of the other, no? And then you can do the chain of variables in your equations. And then I think you are.
Yes, exactly.
Yes. Okay.
When we use the scalar field, we do not look to, for example, here we chose the lapse equal to 1. So if we choose the lapse differently, maybe we can change this relation between t small and large t. We can change it. If, for example, we consider h the third and the lapse equal h the third, I believe we have t small equal to capital T. But this specific choice is appropriate in order we have analytical results.
Yeah.
This is the only reason, right? So we can have many other choices, both lapse and both change of variables. So, but this one is specific in order to have this linear term here.
Okay. Yes. Thank you. Thank you.
But it was a very good. Okay. Thank you. It was a very good point because we can begin already from a stiff matter fluid without talking about scalar field, right?
Yes.
So thank you. In the quantum background, now the second paper with Renato. I'm sorry, it's wrong here. Yeah, no, it's still the work with Victoria. The perturbation is after. I'm sorry, I'm confused. we now consider the Hamiltonian, this Hamiltonian here, with zero potential. But we promote both the scale factor and this new variable t to operators. So the canonical momenta will be operators like in the usual course of quantum mechanics, Schrödinger equation. You have these operators, and now, of course, the Hamiltonian will also be an operator. So we need to operate this operator on something. So we operate it in a wave function. So it's a wave function of the universe, let us say so. And this is the Wheeler-DeWitt equation, the Hamiltonian operating on the wave function equal to 0. So this Hamiltonian that we had here, with two terms, are now written in this form and applied to the wave function. When we organize it, we have this Wheeler-DeWitt equation. Forget about the red term by now. So here is the first derivative with respect to t, the second derivative with respect to a. And this term here is included by hand because we have some ambiguity in defining the ordering of A and PA in the quantum setup, or simply we can change this psi in a suitable way that it does not change the overall behavior, and this term emerges. So we have the freedom to have this term here. So S is a constant, and is the scale factor derivative with respect to the scale factor. I didn't write the details here, but they are in the paper. So if we set equal to 0, S equal to 0, we do not have this term, but we have, if we consider this term and set S equal to 1, this term helps us to simplify this equation. And in fact, if we take it to 1 and change variable A, the scale factor, to a variable chi, we obtain this simpler equation. So this is like a Schrödinger equation for a free particle, no potential. Here, it was supposed to be -1 divided by 2 times the mass. So if you compare, it's like a particle of mass -2. It's absurd, but if we compare, it's something like that. So we have a free particle Schrödinger equation, which can be solved simply, in a simple way. So we consider an initial wave function at the initial time, t equals 0, a Gaussian wave function, which is the minimum uncertainty that we can have. So this equation with this initial condition, we can obtain the solution for psi, which is written in the polar form. We have omega and S a phase. Is a phase. So omega has this form, and S has this form. So this is a complete solution, right? So from here, we have the solution for the Wheeler-DeWitt equation. What can we do? We can take the wave function, for example, and calculate, for example, the mean value of the scale factor. This is an option, like in usual quantum mechanics. But I will not do it. I will consider the Broglie-Bohm interpretation of quantum mechanics. In this interpretation, we understand, of course, the psi squared as the probability density. But this probability density is not like in the usual quantum mechanics of textbooks, which is the Copenhagen interpretation. There, this probability has to do with the collapse of the wave function. We have particle which does not have any objective reality, so it does not exist until you measure. So when you measure, the wave function will collapse, and this probability will set the particle to a reality at a specific point, for example. So the measure is important, and we have the probability of measuring the particle at some point. Here is different. We have the phase of the wave function. The phase will guide the particle in its trajectory. So the particle always has a trajectory. You do not need to measure. Always have an objective reality. And this probability density is the probability of finding the particle in a certain path. So this is like a storage of all possible paths that particle can follow, but it will select one of the paths. So this is a storage. And it has the same features of the usual quantum mechanics. We have the double slit. You have probability of going through both slits and have interference, all the same thing, but with a different interpretation. So here, if S guides the trajectory, sorry, the wave function guides the trajectory. So A is the position, if you say this way. So this is the trajectory, and the guidance equation is the canonical momenta related to A, equal to the derivative of the phase. So this is the wave function. S is the wave function. So this is the guidance equation where the wave function S guides the trajectory of the particle. So in our case, who is PA? PA is here. We can invert this equation. Then we obtain the equation of motion here due to the wave function. And solving this equation, here we have an epsilon, which was not defined. You can see it here in this change of variable. We left it undefined, find the solution for the scale factor, and at the end, we obtain a very awkward solution here, and then we take the classical limit to these solutions, and then epsilon is obtained. So the details are not here, but epsilon is obtained. It's already included here. And if you look to the scale factor, when t equals 0, you do not have a problem. You have a minimum scale factor, which is A0, which we call AB. This is scale factor at the bounds. So when t equals 0, in this square root, you have 1 plus 0, 1, 1 minus 1. So here is 0. Exponential of 0 is 1. So you have AB. This is the finite scale factor. The finite scale factor at the do not have initial singularity anymore. So you have a non-singular quantum bounce, and the Hubble parameter is very awkward. In loop quantum cosmology, you would have this part with the general relativity part, and here ρ divided by ρ critical. In the Broglie-Bohm interpretation, you do not have the same Friedmann equation for each fluid. Here we have a stiff matter fluid. So this is the Hubble parameter, the Friedmann equation, the quantum Friedmann equation. If the fluid was radiation, dust, for all of these ones, we have a different Hubble parameter. So specifically for stiff matter, we have this logarithm behavior here. So when we have ρ equal to the critical density, which we can define, we have general relativity as usual. So this is the quantum bounce in the Broglie-Bohm theory. Oh, and the plot, here we have a contracting phase. Here is where A equals to AB, and then the expanding phase. The usual observed expanding phase, and here the new contracting phase. So now it's like we are merging the two classical solutions. Merging here. They are not disconnected. They connect here. They do not have this part before and not this part after. Right? So this is the main picture of the model. And now, with this model in hand, this background model, we can look at the constraints still at the background level. There's no observational setup here. So we begin with the critical density, which I call rho B instead of rho C. So rho B is the largest critical density that we have at the bounds. So it must be greater than the ones of this specific periods: the Big Bang nucleosynthesis, the quantum quark-gluon plasma decoupling, and the electroweak phase transition. So at this epoch, which happens mainly the radiation epoch, we have this energy density. So the bounce energy density must be greater than the ones of each of these epochs. The temperature Ti is with respect with each of these epochs, also Gi. I do not write it here, and at the same time, we require that our density and energy density is below the Planck scale. We do not need to, the maximum value of energy scale, we consider that is the Planck scale. So we are a little far from this Planck scale. So these conditions lead to a range of rho B. Also, we can define a length scale, which we can obtain from the Ricci scalar. So 1 divided by the square root of r at the bounds, we obtain a length scale given in terms of the parameters of the theory. So first of all, we need that this length scale is smaller than the one of these three phases. So this is a length scale, also length scale of Big Bang nucleosynthesis, quark-gluon plasma decoupling, and electroweak phase transition. So the universe scale must be smaller than the universe have this phase. So this is a causal condition, and like this one, we need that the length scale is greater than the length scale of the bounce. So it's analogous to this one, the second and the second. And now we have this range for LB. We also need to assure that we have a stiff matter domination at the bounce, because from the very beginning, I consider that the potential is 0 during the bounce. So I can say that the energy density dominates. It's the same thing. So if I impose this equation, at the bounce, the kinetic energy dominates over the potential energy, we have this condition here. So it's very important to consider. I forgot to say, to mention a detail. Let me come back here. All the calculations were done for the potential equal to 0. So in principle, this happens for potential equal to 0. I cannot include the potential. But this correction term is only important near the bounce. So it does not matter when this term is relevant if we have potential or not, because it's subdominant. So we can treat the bounce with this term only with stiff matter. But when we go far from the bounce, this term is negligible, and we have the usual GR. So we can put back the potential here. So there is no problem with working with 0 potential and then including it back. I tested it numerically. There is no problem with that. So continuing. The last condition is the minimum number of folds during inflation. So during inflation, you need to have at least 60 folds. So these 4 considerations will constrain the parameters of the theory. We consider this type of potential, the power law potential, for 3 values of when the quadratic, quartic, and sixth. I also consider the stereobitic potential, but it's less restrictive. So I only put here the power law potential. So when we use all these constraints here, we can set the ranges to the model parameters, which are rho B T0, lambda, and AB. So rho B, the energy density at the bounce, is set in this range. T0 is set in this range. Specifically, in this study, we set AB equal to 1, which can be changed after we have freedom to set AB equal to 1. And the last parameter, lambda, is dependent of rho B. So if you have the range for rho B, you have the range for lambda. So this first paper is about the background constraints, and it's done here. Then we go to the second paper with Renato, now, in fact, where we deal with scalar modes. So we do not consider tensor modes by now, only the scalar modes. This is the equation for the perturbations. Here are the definitions, the usual definitions. The only difference in the Broglie-Bohm quantum theory is that the equation is the same, but A is quantum. The only difference. You derive the same story and obtain the same equation. So we need to understand how to compute the power spectrum from here. So we need to solve for mu k. To solve it, we cannot solve in from only one attempt. We need to solve in each of the phases. Which phases do we have? Let me come back to this picture here. We have the bounce here, this region below. Here we have contraction, so contraction. Then we have the bounce, and then inflation. We do not have inflation in the past, only the expanding part. So from the bounce to inflation, there is a connection. The bounce is obtained for a stiff matter. And during inflation, the equation of state parameter is not 1, it's -1. So we need to come from 1 to -1, and we have a transition phase between these phases. So we have what we call here, a transition. So contraction, bounce, transition, and inflation. So we need to solve the modes for each of the phases and connect them, match them. So solution each phase and match the solution. Here I put the equation of state parameter, only a representative plot for a scalar field. When you have the kinetic energy dominating, you have that omega is 1. So here near the bounce, here T equals 0. Near the bounce, we have the stiff matter phase. And at some point, the potential becomes important. Not instantly, but it will become important, and eventually it will dominate. When it dominates, you have minus V divided by V, so omega equals to -1, which is here, -1. So when we transit from kinetic energy domination for potential energy domination, we have this phase here. This is the transition phase, right? So we need to solve for each one. This equation, when we solve for the contraction phase in the far past, we do not have great variations in the scale factor. So k squared dominates, and so we have plane wave solution. And in the contraction phase, we need to, here, very far past, we need to define a vacuum where everything begins. We define the Bunch-Davis vacuum. So the solution for the first phase, the contract phase, is the Bunch-Davis, which has no particle production. We do not have the other term exponential of plus I, K, eta. No, only this one. This is the Bunch-Davis vacuum. So where everything begins. Then we go to the bounce phase, where the scale factor is specific and is given by this one. Let me come back. This is scale factor. So if we derive it twice, it will be a giant expression. In fact, it is. So here we have the second derivative, and here is the result. We cannot integrate this equation, this equation with such a big term. So we perform an approximation, which is the Post-Teller approximation. We parameterize this expression by a simpler one, which has two constants, V0 and alpha. And by matching these two, we obtain V0 and alpha in terms of the parameters of the theory. So this potential here approximates very well this one here. We have a plot in the paper. So this potential, when we use it in the equation for the modes, it can be solved analytically. So we have the modes here in terms of hypergeometric functions. I have time. I still have time.
No, you are okay. There is no problem.
Thank you. Okay. So we have this the solution for the bounce. Then we have the transition phase where we are far from the bouncing, but in the future, between inflation and the bounce, far from the bounce. So this term here is not big, so it's plane waves again. And we have this solution here. And finally, you have inflation, where the modes are solved in the literature. There is nothing to consider differently. So these are the modes for inflation. So we need to match them. When we match the first to the second, we obtain the coefficients here, ck and dk. When we match the second to the third, we match and obtain alpha tilde and, A tilde and B tilde. And finally, we match with alpha and beta k and obtain the parameters in the inflationary modes, which are the ones that we will use to compute this spectrum. So we are done with this calculation of obtaining the two parameters. So the power spec,
sorry, Professor. I'm trying to understand how you are introducing the quantum prescription, no? The quantum cosmology prescription for perturbation, but you are using the background to use to solve with the quantum corrections and putting that solution into the Mukhanov-Sasaki equation. But,
yes, the Mukhanov-Sasaki equation.
Okay, but you are not deducing this from the action, not?
No, the Mukhanov-Sasaki equation for the quantum setup is exactly the same as the classical one here. Exactly the same. So the only thing that changes is the quantum scale factor. The A, not classical, it's quantum. It's the only thing that changes.
Okay. The scale factor is quantum. Is the quantum solution?
Yes, exactly. This is the scale factor, which has a quantum solution because we invoked this interpretation here. It's the only change.
Okay.
Right? It's in fact very simple. You do not need to calculate totally new equations for perturbations.
Yes, like for example, using the second order action, deducing the second order Lagrangian and the Mukhanov-Sasaki equation is not necessarily, but
no.
Okay, but when you are treating the perturbation, you are proposing some perturb metric. In that case, you
Right.
had the scale factor, and then the quantum effect is coming from the metric.
But here the space-time is quantum every time. We have a quantum space-time. We do not need to perturb the classical one, for example.
Okay.
From the scale factor is quantum, so the background is quantum.
Okay.
It's quantized, right? This is a very subtle difference, in fact.
Okay. Yes, you are perturbing the quantum background in the
Yes.
standard way, using the same degrees of freedom for GR. There is no more degrees of freedom. Okay, good.
Exactly.
Okay.
Exactly.
Okay.
So we are lucky that the equations are the same.
Okay. Yeah.
And do not worry about any change in this setup.
Okay.
Right. So thank you for the question. I will continue from here and about the power spectrum. So we obtained the coefficients of the inflationary solution for the modes. And when we compute the power spectrum, which is this expression here. We have the modes here. When you compute it, we have, without the details here, we consider, we do not consider anything. We have the power spectrum of GR multiplied by this term here. So in the paper, you have the full calculation, but we here simply write that the power spectrum of GR, the usual one, is corrected by this function here, which has to do with alpha and beta k. So this is a correction, a function of k. So the spectrum, which is nearly in scale invariant, now has a modulation, which can destroy the scale invariance. So we need to understand what happens here. So this term needs to be detailed. So we parameterize this term here in front of PGR as 1 plus delta k, and delta k is given by this expression in terms of alpha and beta. So we need to calculate this term from the expressions here. So when we calculate it, it's very big. Delta is given by these two lines here. And of course, when delta is 0, we have that this term is 1, and we have the usual GR spectrum. But if not, we have delta difference from 0. We have these two lines. This second line has a cosine at the end, so it oscillates. And here is a phase that's defined here, but it's not important. This cosine, the line involved, the cosine oscillates rapidly. So the only contribution is to oscillate. And oscillation is not relevant. We need to compute a mean value, average. When we average over time, this contribution is negligible. So this whole second line is negligible. And we keep only the first one. We have a plot for this situation. In fact, it only oscillates around the mean value. So this is the important expression. And this expression is given in terms of C and KB, which are new parameters, but not necessarily new. C is defined in terms of the old ones, lambda T0 of the theory, and KB is defined in terms of AB, lambda T0, all the usual parameters. So nothing different, only a beautiful way to write it. So considering that this is the change in the power spectrum, we look at this term here, this hyperbolic cosecant, KB divided by KB. When K divided by KB is much greater than 1, this term is negligible. It's not negligible only when K divided by KB is small. So this is not 0. So this hyperbolic cosecant squared is not negligible only when K divided by KB is smaller than 1. So when K is smaller than some KB, this is where quantum gravitational effects of the bounce are relevant. So this is a parameter defined at the bounce. So this is an effect of the bounce, a quantum effect. So this is the important region of K, small k, which means large scale, which means low multiples. So this is the region. Let me come back. I will not do it, but I will do it. In the second or first slide, observable signatures. In which region we see observable signatures? In the low K, in the large scale region of the power spectrum. So this is the answer. So understanding that we have the small k, we need to know who is the upper value, the value of kb. If k needs to be smaller than kb, which value is kb? So for the analysis, we choose prior ranges to C and kb, which are the parameters here, from the background analysis, because we already had ranges for the parameters of the theory. So from the background analysis, we have this range for C. And at the first paper, we considered that AB was equal to 1. We can recover the arbitrariness of AB by some rescaling, so AB is arbitrary again. But due to this arbitrariness of AB now, KB has no prior range. So KB is free, we'll choose a broad prior range and the range of C. So what we do, we consider some representative values of this range and then constrain KB with respect to observation. So this numerical analysis will look for the scale-dependent function delta during the biospectrum. We use the data from Planck 2018. Use the modified code CAMB, which is in this paper. This part was done by the collaborator Nicole Benetti from University of Napoli. So the details are given by her, and these are the data that we used, and the lambda CDM cosmological parameters, which are also included. We consider broad prior ranges also to do not miss anything. And the representative values for C are these ones, and these are the prior ranges for KB. -7, the low limit we choose it by our mind, from our mind, and the upper values are to be consistent with Lansing normalization. So the upper limit has some physics. So by considering these values of C that I mentioned before, we have computed all the relevant quantities, AS from the power spectrum, scalar power spectrum, the running, the famous H0 and sigma 8, and also omega m. The most important fact is that all values here are consistent with observation. So our model is consistent. We have a consistent model of bounce plus inflation. We can do it. But we can only have inflation, only have a bounce. Okay, we can have this theories, but we also have a consistent bounce plus inflation theory. No problem with that. So the model remains compatible with data, and now we can obtain an upper limit for KB. So this KB here that we consider that K must be smaller than KB, now we have these upper limits. So the modes K must be smaller than these values of KB. Of course, they change for each value of C, but we have upper limits for each case. So the current observations constrain the upper bound of KB, and it's very important. We know that from KB to smaller values of K, we have changes in the power spectrum. So changes in the large scale structure. And a comment about the tension between H0 and sigma 8, there is a correlation between them. When one becomes bigger, the other becomes bigger, and the same for smaller. But here, when we consider two values of C, these ones here, the second and the third, you see that H0 is the same for both of them, but sigma 8 changes a little bit. It changes within the numerical errors, but it indicates that maybe there is an anti-correlation in this model. Of course, we only consider one potential, the power law potential for quadratic, quartic, and sextic. And if we look for a range class of potentials, maybe can show something different, right? So alleviates this correlation. But we do not have a robust conclusion here, because it's not out of the numerical errors. And we obtain KB from, we have the definition of KB, and we can write suitably this form, in which KB is a function of the total number of e-folds. So we take this expression here for KB, and we can define, after this rescaling that I mentioned, on lambda and T0, we can define KB in terms of the total number of e-folds from the beginning of the bounce until today. So from the bounce to today, the number of e-folds. When we compute it with all the ranges we have a total number of e-folds of around 124 to 26. So this results being that we have 6 e-folds of inflation, at least 6 e-folds from the end of inflation until today, the present epoch, which is necessary, and it remains 4 to 6 e-folds from the bounce to inflation, which is the pre-inflationary phase. So this is important, very important, because when we perform the background analysis, which has nothing to do with perturbations, has no cosmological data, the theory, the theory predicts that we need to have 4 e-folds in the pre-inflationary phase, and the observations do the same. So independent conclusions, which are the same, this is a very robust result. In loop quantum cosmology, I believe that we can have 21 in the same setup, 21 e-folds of inflation, e-folds in the pre-inflationary phase. But so the two models are competitive, if we say this way, but both are consistent in this point of view. So finally, bounce plus inflation is consistent with cosmological data. There is a tendency, it's not guaranteed, to uncorrelate these two quantities. And we have a potential way to test cosmology at Planck scale, because we have a spectrum of inflation which is connected to the bounce. And these initial conditions are taken at the contracting phase. So we are taking the universe, the very, very early universe, right? And finally, we can compute in this theory particle creation, particle production by the Parker mechanism. In the bounce, we have particle production. I have already done it in loop quantum cosmology, for example, and now the student Renato will perform this calculation. And we can also look for the anomalies in the CMB, because if we have a correction at the power spectrum here for low k, this means larger scales, we can look for the anomalies that we have for low multipoles, L equal 2, the quadrupole, and L equal 3 with the non-Gaussianities. We can look for constraints of the theory in this region. So it's a very interesting subject to investigate. So these are two ideas that we will do in the next months, and we expect to obtain good results. So that's it. Thank you very much for the opportunity.
Thank you very much, Professor, for your very nice seminar. Very interesting the seminar, and yes, I think it's going to be very useful for all the students here. I don't know if yes, and for us also. I don't know if there are some questions from the students, from professors.
I have some detail that I wish to include if I have time to do it. It's not part of the seminar. Can I do it, or do you have time?
Yes, of course.
A very interesting detail is that when we have inflation, the most important modes are the ones which leave the horizon, what we call the horizon. So k squared initially is greater than this term. So these are the modes that are inside the horizon. As this term increases, k squared becomes smaller than this term here. So the modes which are initially with great K become with small k with respect to this term, and they leave the horizon. And these modes that leave the horizon are the relevant ones for the power spectrum. At the bounce, we have something similar. At the bounce, this term is like a barrier. So far from the bounce, k squared dominates. It's greater than this term. Near the bounce, this is a barrier. So when we approach the bounce, k squared is smaller than this term. So initially we have modes inside the horizon and then outside the horizon. So horizon crossing again in the contracting phase, and we have the power spectrum of bounce, pure bounce. When we have bounce plus inflation, we have inflation, first of all, at the same way, but the modes at which inflation begins are not the bunch days. The modes are they were already being cooked by bounce. So when they come to inflation, they are not bunch days. They are already squeezed. So when you have pure inflation, you have bunch days vacuum and the power spectrum. When you have bounce prior to inflation, the modes come not bunch days, and that's why we have this correction here in the power spectrum. So I thought it was relevant to explain.
You are changing the vacuum then, the vacuum
Yes,
solution. Yes.
the vacuum of inflation.
Yes. Okay, I have a question about this because yes, it's very, I like this. It's very interesting. And also, no, inflation yes, is a paradigm, no? Currently, is the best paradigm explaining
Right.
the problems in the standard cosmological models, but also is providing us some mechanism, no, to generate the quantum fluctuation, the seed, no, for the structure formation in the universe. The anisotrope is in CMB. But also, I think the most important prediction for inflation, which is going to be like yes, a very important yes corroboration of the model, if the prediction for the gravitational waves, the primordial gravitational waves.
Right.
But all yes, because in detecting the primordial gravitational wave, we are going to know exactly what is the scale of inflation. In here, for example, you are mentioning the scale of inflation, but really we don't know exactly what is. And then perhaps yes, could be bigger, and then we are more in like close to the quantum scale or not. But indeed, this is going to be relevant also for these bouncing models. Okay,
Of
but
course.
but in any moment, you speak about that, about the perturbation, the tensor perturbations, and then also, for example, if we have the quantum correction to the background, these quantum correction are going to appear also in the Mukano-Sasaki equation for the perturbation, for the tensor perturbations.
Exactly. The perturbation, the power spectrum, the PT here will be exactly the same. The very same correction will be present in the power spectrum of tensor perturbation. We do not do the analysis for the gravitational waves because we don't have data. We have only upper limits, right?
Yeah,
So we
yeah.
can do it, for example, for upper limits. This
Okay.
is maybe a work in progress with a collaborator, but we do not pursue yet in the subject. But in fact, we have PT, this term, PTGR.
Yeah.
So, for example, the tensor to scalar ratio does not change because this term cancels out. This is the same. But the power spectrum itself from the gravitational waves, if we have data, we can do the same analysis here.
Yes, yes, it's like the term is a smoking gun, no? For inflation, just
Yeah.
the tensor perturbation, but yes, but even for example, if we have only yes, I know some upper bound only, Usually, when we treat this inflationary model, we use this upper bound to put a constraint on the parameters. And now, for example, with the ECT, we have also constraint on the running. And then usually
Right.
we saw, for example, the last time doing some paper with the students, that sometimes our model was correctly about the scalar power spectrum and the tensor power spectrum using Planck 2018 in BICEP. But when we contrast the result of the prediction for the parameter with the running, we were outside the contour. And
Outside.
then, yes, and then in that moment, yes, we saw, no, yes, we need to impose also the running, the constraint for the running coming from the ACT. And then, and was in this way,
Right.
no?
Right. Yes, I would like to do more details. For example, the gravitational waves. I did not do anything with gravitational waves. It's a open work to be done, even to collaborate,
Yeah,
because I didn't write anything about only speculation.
yeah. Okay. Okay, thank you, Professor. Are there any questions from the
Yes,
students?
very good.
Yeah, I got a small question. Yes, I got a small question. Okay. So, although your model seems to be compatible with Plan 2018 data,
Right.
it seems that it's not a statistical preference over standard lambda CDM model. So my question is, what kind of observation signature do you think will be necessary in order to distinguish this scenario in a compelling way?
Right. What I think exactly the the gravitational waves will be important, and also this the anomalies. The anomalies will be relevant because if it fits well with the anomalies, it will be a great advantage of the model, of course. But I believe the way it feels the gravitational waves will be the most relevant way to distinguish the model by now. That's it.
Okay.
Thank you.
Thank you. Also, the students, there are now, we have some
Yo
students.
tengo una, profe.
Okay, that's good.
I will try to ask in English. Probably you say in some part of the presentation, but for me it's difficult to understand all in English yet. But I wanted to ask
We have the record
about
para
the.
to see
I
again in
understand
you.
this.
What?
The model predict a bouncing, I understand, but if it exists some signal in the CMB, I ask it because when you present the power spectrum after, appear a lot of in the next part, yes, and in the delta key appear a lot of coseno hyperbolic, so represents a lot of oscillation. I understand, right?
Yeah, this is not an oscillation. The hyperbolic cosecant is not an oscillation. Here it is an
Okay.
oscillation, but the C is constant. So this term here is in fact an oscillation because you have evolution here, right? We have different values of K, we have more details, but here it's not an oscillation, right?
Okay. Thank you.
Okay. Another question is about yeah, you are using the Broglie-Bohm interpretation, but we have another interpretation in quantum cosmology, like the many worlds interpretation, for example, no?
Yes, I know.
Yes, the Copenhagen, I don't know if it's the same. There is
No,
some,
no.
it's
Many
another.
words, I think it's the Everett interpretation, I believe.
Yes. And then how this is sensitive to this interpretation, for example, these results.
I don't know. I didn't do the
Okay.
calculations,
Okay.
but it would be interesting to investigate in other because we have different. If we have different quantum theories with similar results, it will be interesting. Universal behavior, but I didn't consider this
Okay.
theory. You have other theories for consistent. I don't know the name now, but there are 3 or 4 quantum theories that could be considered differently.
Okay. Okay. I know Professor, I think it's Nelson is Pinto, Professor
Nelson
Pinto,
Pinto Neto.
Nelson Pinto Neto, yes, in CPF. He works,
Yes.
they work a lot also with this, with quantum cosmology. I think they work with this, the Broglie-Bohm interpretation, but I don't remember now. I saw another paper from them working on another also. Uh, but yes, I think yes, this is very interesting. Do you know him?
He was my supervisor as
Your
postdoc.
supervisor? Ah, okay. Okay, good.
I learned everything from him.
Yes, yes.
The bounce, the Broglie-Bohm. I worked with inflation, then
Okay.
I switched to bounce, and then I merged both
Okay.
to learn from both of them.
Okay, good. Okay, yeah, I remember because we performed some paper before the past year with some student, like just with Andres, no? And then I remember in some moment we were solving the Wheeler-Dew equation. And then we need
Right.
to solve, for example, the function, calculated just it was not easy because the equations was very complicated with function like Bessel function, integral function, or integral solution, okay? And then calculating like the probability of the expected value for the scale factor or just for the canonical variables like the scale factor in the field was very difficult. But I remember in that case, the idea was to calculate, yes, the expected value for these canonical variables, which are operators, and then using the correct measure, because the measure can be modified depending on we have another effect, like, for example, rainbow gravity effects or another kind of modifications, depending if we have, yes, GR or another theory. And then, but I remember, yes, we calculated that numerically, and then we studied just the classical limit. And then the
Right.
idea was to connect these results from the Wheeler-Dew equation with the post quantum phase, like in inflation, just connecting the quantum with inflation, yes. And then, but in this case, I didn't see this calculation from you, no? You didn't solve the Wheeler-Dew equation exactly. I don't know. I didn't see that.
Now the Wheeler-Dewitt equation was solved
Calculating the
exactly.
wave function, but or because it's because the interpretation that you are using, perhaps, I don't know.
Yes, yes. It's easy to solve the Wheeler-Dewitt equation. This change of variables
Ah,
here
okay.
is the
Okay.
important part. If you do not have this type of equation, it would be very difficult to obtain the propagator and solve it. But this is very simple. There are other cases when we can obtain the propagator and also solve, and there are situations where we cannot solve, so we perform a separation of variables.
Yes,
We
yes,
choose
yes,
functions, specific functions that we can integrate,
yeah, really.
and we have a glimpse of what happens. But here is the exact solution. Due to
Okay.
this initial condition, everything is done in such a way that we have this exact solution. But for example, we can change the initial condition. We can have, for example, non-Gaussian initial condition. It may lead to I'm sorry, I don't remember the word, asymmetric symmetric bounds, different in the past and the future. We uh, can change the initial condition, and we also can obtain an analytical solution. But these cases where we choose the functions, I didn't do, but I know in the literature.
Yeah, yes, perhaps
This is what you mean.
yes, in our case, yes, perhaps in our case, we were using the many words interpretation, and then we need to integrate the expected value for the operators.
Yeah,
In this case,
exactly.
you obtain some exact solution. If we, and you, you haven't the limit, taken the limit, the limit, not the classical limit in some moment. Yes, you haven't taken the limit, the classical limit. I think,
Yeah,
no?
the classical limit is natural because we have
Yes,
the quantum scale factor, which is quantum near the bounce. When we go to the expanding phase, the scale factor naturally goes to the classical one. So the coherency is natural in this
yes,
case. We don't need to worry about it. It happens and then we don't see it.
yes, yes. Okay. I don't know. Are there any questions from the students?
Uh, I have just a small question, Professor.
Yes. Yes.
Um,
Right?
I was I saw that in your presentation, you in your paper also you used only the analysis with the um, with the Planck data. So like the H naught value is like within the Planck region only. So like can you comment on the H naught tension that we have? How does the our bouncing model, this bouncing model, like can elevate or have some proposed values, or maybe prefer the Planck value more, or something like that?
You mean about the tensions, right?
Yes, yes, H naught tension, yeah.
Right. Well, what we have here is not so robust in this aspect of the tensions. We have a small idea about it. We have that H0 and sigma H, which is the parameters involved in the tensions, are for the model, for the specific choices that we did, are within the expected values. So here is H0. We do not have any problem with the values. So this is the only result about it. The sigma H also. The only fact is that we have this idea of anti-correlation. So the sigma H is changed while H0 is not. It's the only thing. We do not have any another aspect, a relevant aspect about these parameters. Only if we consider other potentials. Maybe for other potentials, for example, H0 is off the the permitted region. I don't know. I need to improve the calculation then for other potentials, right?
Okay. And also, I was looking at the triangular plots for the analysis, and I mean, I'm not very proficient in this, but like the correlation, the correlation that was in between H naught and sigma naught here in the paper is, it's almost like looks like non-correlated. So
Oh, in
it
this, I'm sorry. Continue, please.
yes, yes, yes. So no, no, I'm just saying that you said that there's like a small anti-correlation between the H naught and sigma 8. So like it looks very very small from the naked eye point of view. So I was asking, is it some like kind of a statistical error, or like is it the artifact of the model?
Now, yes, if we when we look at the errors, we see that
Yes.
these differences are within the error. So it's just an indication that a tendency. It may not exist this difference because it's
Okay.
within the error. Exactly.
Yes, yes.
But this is a thing that we should consider for other potentials. Maybe for other potentials, this change is not within the numerical errors. So this is
Okay.
why I call it the tendency,
Okay.
potentially broken. There is no robust result about it. There is no correlation. We can say so.
Okay. Okay. Thank you, Professor. I understand.
Thank you.
Okay. Thank you, Nitesh. Okay. Eduardo, do you have any question? You are working on some model, on quantum cosmology. We are trying to implement this quantum the description for f of t gravity theories. Because yes, it's no, this in that case we use some torsion instead of curvature, and then we can add some scalar field also, and we have f of t phi gravity. And then the idea was to how to implement this, for example, this kind of description in these theories, because in that case we need to have an scalar field because the theory cannot explain inflation without an scalar field, like in F of hard gravity, for example. And then also, yes, how to solve the problem with the time, for example, because all the time we saw, no, we need to introduce some perfect fluid, and then we are going to have T plus scalar field plus a perfect fluid, and then the system is going to be more complicated still. But now I think this was very interesting because we can do something similar to your paper, to your work,
Yes, of course.
introducing the time in this way, no?
You simply change the Hamiltonian and do the math here.
Yeah,
The Hamiltonian will change here,
yeah,
and you have a time variable, and that's it. The only problem is to solve the William interpolation.
yeah,
Only problem, the only task.
yeah, yes. Eduardo, do you have question or about you are working? Okay.
For now, no, Professor.
Okay.
I need to study more.
Okay.
You can email me whatever you want. The emails here. I
Okay.
like to receive emails.
Okay. Okay. Thank you, Professor
Uh,
Gustavo. Okay.
So just a small thing I wanted to ask, Professor.
Yeah.
I saw that you told that the analysis that you were doing, you did some modification in the CAM code, and then you did the analysis. So I just wanted to ask, like, is the code that you like made the changes in the CAM, is it on available publicly or no?
I don't know because only Nicole knows it. They change the code. I can talk to her and ask if the code is available if you want. Okay?
Okay. Because I was also like trying to do some like changes in the I wanted to do I haven't done anything yet, but I wanted to like modify the camp also for like
Right.
other modified gravity theories, just like our FT and phi theory. So if in
Yeah.
future if we want to do some analysis, so it would be a like a nice reference for that.
Right, of course. If you email me, I can talk to her and tell you the
Okay.
details.
Okay.
Okay?
Thank you, Professor.
Thank
Thank you.
thank you. Thank you, Nitesh. Thank you, Professor. I think we can close the seminar. And then, yes, thank you also for your very nice, yes, for your kind, no, way to teach, to just to show us, to show for us, no, these results and also your disposition also to write you, no, to email you, no. And then thank you very much. And then of course we are going to email you, no, to mail you in some moment. I think the students or perhaps me also. Okay.
We
And
appreciate.
then
We appreciate.
okay. Thank you, Professor.
Thank you very much
Okay.
for the invitation. It
Okay.
was a pleasure to talk to you.
Okay. And then we are in touch. Okay.
Okay.
Thank you very much.
Thank
You
you.
also.
Bye bye.
Bye bye.
Bye bye.
Bye. Thank you, Professor.